Activation energy, what is it? And what is this Arrhenius equation that has to do with it? Well, I like to think of activation energy as the coffee of chemistry. Now, what that means, I hope you'll kind of see momentarily. So, activation energy is simply the theory that there is some finite energy barrier that must be overcome for colliding particles to react. Just like for you, it might be coffee. For me, it's my black tea that I drink in the morning with plenty of caffeine. It provides that energy that I need in order to interact with the world. And so it's the same way for these molecules. Before they can become a product and react with other particles around them, they must go over some hump that takes energy to achieve in order to go ahead and create that product on the other side. So it's just like this carnival game here. The first hump, it's an energy barrier that must be overcome in order to get to the other side. So the activation energy is simply that amount of energy that must be overcome in order to produce a product. Now there's a couple pieces to this. Number one, the molecules must collide in order to react. You think it makes sense, and it does, but there's so much to this. They have to collide, and they have to collide with the amount of energy necessary for them to react. If you increase the temperature, that's going to increase the energy. It's also going to increase the number of collisions. And so by increasing that temperature, you're giving it enough energy in order to overcome this energy barrier or this energy threshold. But also we have to consider the orientation of the molecules. If the molecules can only interact via one face or one orientation, if they always interact backwards or sideways, they're not going to create the product that's necessary. And so it's really a combination of the correct orientation with the correct amount of energy that's going to lead to a reaction. And so this concept is simply activation energy. Here are the three equations that go with the activation energy. These are the Arrhenius equations. It's all the same equation, it's just algebraic rearrangements. And so if you take the first equation, which is our most true or the simple form of the Arrhenius equation, that's not really helpful. Like we talked about for the integrated rate laws, it's nice to have a y equals mx plus b format. And so the second equation that you see here is that format, where y is your natural log of your rate constant, your m is negative your activation energy over r, which is your gas constant, your x is 1 over temperature, and your plus b is that plus natural log of a, where a is simply a steric factor times your collision frequency. And so it's a constant that is going to depend upon the molecules that are reacting and how they're reacting in space. So how quickly, how often they interact, and what steric hindrances or what orientation is necessary for them to interact. It's just a constant. And so this form is very helpful in graphing because you can graph a whole bunch of different temperatures versus their rate constants, and you'll be able to extrapolate the activation energy from that graph by just looking at the slope. So that's very helpful. But let's say you know your activation energy, or maybe you have two conditions. So maybe one temperature and another temperature that you're doing this study at. Instead of a whole bunch where you've got a nice pretty calibration curve, maybe you're only looking at two conditions. And so in that case, we can set the natural log of A from one set of conditions equal to that for another, because it's supposed to be a constant. And so in doing that, you're setting the whole rest of the equation equal to each other, and you can algebraic manipulate that equation to form this third form of the Arrhenius equation. Go ahead, try and do that. Do the math. It's kind of fun. But that last equation is helpful for comparing the two conditions. The important things to note here is that K is your rate constant, and once again, your rate constant units are going to depend upon the reaction taking place. R is your gas constant. It is the 8.314 joules per mole K. The reason for that being is energy is in joules. Your T must be in Kelvin for temperature. Your EA, now I see a lot of people think that maybe that E I messed up and it's actually the natural log E. It's not. EA is the one abbreviation for activation energy. E and A go together. Neither is a mathematical principle. And so these are all the different formats for the Arrhenius equation, and we can practice either using the second equation and some graphs or the third equation and two conditions.